Hello and welcome to another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 11, Lesson 7 on outliers. Maybe the best piece of terminology in all of mathematics. You know, the name itself almost like tells you what it is, but let's get into exactly what an outlier is right away. Data that is collected to answer a statistical question often has clusters, right? It groups together around some kind of central values. You know, sometimes there's some peaks, sometimes there's some gaps in the data. That's all good, right? But sometimes we have values that lie far away from the center and from all the other data values. These data values are known as outliers. Like literally, data values that are just so strange because they lie way far away from the other data in the data set. All right? So outliers are simply values in a data set that lie far away from the median, often with large gaps between the value and the rest of the data set. So that's kind of key. There's got to be like gaps between that value and the other data values. So let's take a look in exercise number 1. 10 people are taking a trip to the zoo. Their ages are below and on the dot plot. Letter A, which data value is clearly an outlier? Why do you think it exists? All right, well, why don't you go ahead and take a look at this problem and see if you can answer letter A. Well, I'm pretty sure it's this one, right? We've got this cluster of data, right? A cluster is just kind of a grouping together of data. We've got this cluster of data, a huge gap between the largest one of these, which is at 8, and the next one over, which is 26. So, no great surprise, the 26 is an outlier, and it's probably because, because that is a chaperone. A chaperone or a teacher or an adult or whatever you want to say that's taking the kids on the trip, right? It makes sense. I hope you're not going to have a bunch of 5 to 8-year-olds going to the zoo by themselves. You never know, especially at these times. But yeah, so you have this chaperone. All right. Now, what's the point? Outliers can do some weird stuff, especially when you're trying to answer a statistical question, right? If the question was, hey, how old were the people that went on this trip, right? Then you might want to give the average age of the people on the trip, right? So let's take a look at the mean age of the people in this group, both with the outlier present and when we exclude it. So let's take a look at letter B. If you exclude, leave out the outlier, what is the mean age of this group? All right, so I know you've got the data above. I decided I wanted to reproduce it here so we didn't have to keep moving the screen up. But literally, my point here is, let's say we cross this out. So instead of having 10 values in our data set, we now only have 9. I'd like you to pause the video and figure out what the mean or the average of these data values are. Pause the video now. All right, well, let's add them all up. What do you have? We have 5, 5, 5, that's 15, plus 6, which is 21, plus 6, which is 27, plus 6, 33, plus 6, 39, plus 7, 46, plus 8, 54, right? So when we sum all of these up, sum all the ages, we get 54, all right? Then if I do 54 divided by 9, right, that's going to be our mean, also known as our average, right, we're going to get 6, right? And that makes a lot of sense. 6 years old is the average. That makes sense, you know. If there's no outlier in here and we've got a bunch of 5s, a bunch of 6s, a 7 and an 8, 6 years old makes all the sense in the world. But what if we include that outlier? That's letter C. If you don't exclude the outlier, what is the mean age of the group? All right, so same song, second verse. I'd like you to now find the mean of these 10 values. And by the way, you already know the sum of the first 9, so maybe just add the 26 to the 54. It'll make finding your mean a lot easier. Pause the video now and find the mean with the outlier included. All right, well again, I'm gonna take a little shortcut here because I already found the sum of the first 9. So I'm gonna take 54 and I'm gonna add my 26 to it, and that's gonna give me 80. So now my mean is gonna be 80 divided by 10, which is equal to 8. Now, before we go on and take a look at the medians, I really want to point out why it would make more sense if we wanted to really answer the statistical question, how old are the people who went to the zoo, right, on this trip, right? Why we might want to exclude the outlier instead of including it, right? It would be a little weird looking at this dot plot to say that the average age, the mean age, was 8 years old, right? Here is 8. Right? There's 8 on the number line. Right? The average really should represent most of the data in the data set. But there's only 2 data values that are either at the mean or above the mean. All the rest of it's below the mean. Right? All the rest of it's below the mean. But that 26-year-old, right, is literally what we call pulling the mean up. It's dragging the average up. As opposed to when we exclude the mean, right, or sorry, when we exclude the outlier, this is the mean. And it would be much more reasonable if I said, hey, how old are the people that went on this trip? If you said, well, you know, their average age was 6 years old, that would be way more representative of the age of the vast majority of the people in the group, right? You know, excluding this person, yeah, 6 years old is a good way to describe the average age of people going on this group. Saying that the average age is 8 years old seems highly questionable given that the only 2 people that are 8 years or older are the last 2, right? Now, let's see what the effect of an outlier is on the median. Letter D. Do the same analysis for the median of the data set, both with the outlier excluded and with it not excluded, all right? All right, so let's come back to this. Here, I've actually given you the 2 data sets, but I've literally gotten rid of the 26, and here, the 26 is still there. What I'd like you to do is figure out what the median is for both of these cases, one where we've tossed the outlier away, and one where we've kept it. Pause the video now and take a few moments to do this. All right, well in this case, right, we've got 9 total. So 1, 2, 3, 4, 1, 2, 3, 4, right? 4 above, 4 below, the median is equal to 6. Now let's take a look at the data set where we haven't excluded the outlier, right? That's got 10, right? So since it's got 10, I can just go 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. The median has to lie right there between 6 and 6, which means the median is also 6. Right? So it makes answering this question very easy. Did excluding the outlier make a difference on the median? And the answer was no. All right. So what's the big picture here? Right? Outliers are very unusual data points that lie in a data set. And they can really throw the mean off, the average off. They can either make it higher than it really should be, as it was in this case, because we had a very high valued outlier, or it can make it lower than it should be because we have a very low outlier. On the other hand, outliers have hardly any effect on the median, right? The median is the middle number. And whether your largest number or your smallest number are way away from the data set really isn't going to have much of an effect on where that middle number is. In fact, it had absolutely no effect in this particular data set. So, moral of the story is, if you've got outliers, probably the best measure of center is the median and not the mean. But let's keep working with this idea. All right, outlier effect on the mean and the median. We just kind of talked about this, but let me reiterate. Outliers will tend to have a significant effect on the mean, the average, because of how large or small they are compared to the other values. Outliers tend to have a small effect on the median, or no effect at all. So in data sets with outliers, the median tends to represent the center much better than the mean. Let's take a look at exercise number 2. Let me bring it up to the top so it's easier to read. Let's take a look. High temperatures on May 1st in New York City were sampled for 15 different years in the last century. The data was the following. Letter A, what value appears to be an outlier? Now again, before we get into this, let's kind of frame a statistical question, right? Maybe the statistical question that we would be wanting to answer here is, how warm is it in New York City at the beginning of May? Right? How warm is it? And we oftentimes measure how warm it is by the high temperature that we reach during the day. So maybe you go out and you sample, 15 high temperatures on May 1st in New York City, and here they are, right? Letter A, what value appears to be an outlier? This should be pretty easy. Pause the video now and write down what you think the outlier is. All right, well, 40 degrees, right? Look at this gap. Look at this huge gap between the second smallest temperature at 66 and the smallest temperature at 40. So, yeah, right? Huge gap, right? This big gap. Again, if we had a small gap, we wouldn't consider it an outlier. If we had this thing and it was sitting maybe at 60, I wouldn't really particularly consider that an outlier, even though there might be a gap between the 60 and the 66. But between the 40 and the 66, that is such a large gap that that 40 is an outlier. Now, letter B. What is the median of the data set? All right, go for it. We know that outliers don't have much of an effect on a median, so we're not going to exclude the outlier. Why don't you go ahead and figure out what the median is? Well, since we have 15 years, right, if we subtract 1, take it down to 14 and divide by 2, right, 14 divided by 2 is 7. That means we'll have 7 values below the median and 7 values above the median. The median, therefore, will be the 8th value. 1, 2, 3, 4, 5, 6, 7, 8. This has to be the median because there are 7 values here. Let me just count. 1, 2, 3, 4, 5, 6, 7, and 7 values there. So the median is equal to 70. Now, let's talk about letter C. Will the mean be lower or higher than the median? Justify without first finding the mean. All right. So in other words, without even calculating the mean, I claim that you can tell me whether or not the mean will be higher or lower than the 70 based on the fact that our outlier is sitting there at 40. Pause the video now and make a prediction. Well, the mean will be much lower. Well, I shouldn't say much lower, but the mean will be lower than the median because the outlier is much smaller than the rest of the data. I'm going to take up some room from my other problem. That's okay. We'll find the space, right? So whenever the outlier is far above the rest of the data, like we saw in exercise 1, the mean tends to be higher than the median. When the outlier is much smaller than the rest of the data, then the mean tends to be much lower than the median. But you don't have to take my word for it. Let's actually calculate the mean. Let's take a look at letter D. If the sum of the data values is 1020, and trust me it is, then what is the mean temperature? Does this support your answer from C? All right, great. Why don't you go ahead and find the mean temperature? Now, the hardest thing about finding means is actually summing up all the data. So I'm really hoping you did not spend time adding all these up. That's why I gave you this number right here. Now, since I already know the sum is 1020, to find the mean, all I have to do is divide 1020 by 15. All right? So let me get myself a little bit of room here. 1020 divided by 15. Well, let me see. I mean, this is kind of some obnoxious long division, but whatever. We'll go with 6. Let's see. 6 times 15 is 90. I know that just off the top of my head. That puts me at 120 down here. Let me think. I think that's 8, but let me check. 8 times 15 is, or 8 times 5 is 40, and then 120, subtract, and 0. You got it. So the mean is equal to 68, right? Our median is equal to 70. Our mean is equal to 68. So does this support your answer? And the answer is yes. Now again, take a look at this just for a second, right? Look at this data set. We're trying to answer, some statistical question like how warm is it at the beginning of May in New York City, right? And you could easily say, based on this data set, the median temperature is about 70 degrees. Now, it's not like the mean is really, really far away from the 70, but if you looked at where 68 is on this number line, right? That's where 68 is on this number line. Look at how much data is above that. There's a lot more data above that than there is below that. So it would be weird to say that the mean temperature, the average temperature, is around 68, given that actually most of the temperatures, right, the vast majority of the temperatures are above that mean. So that would be misleading, right? On the other hand, if you said, the median is 70, well, now that makes all the sense in the world. Half the temperatures are above 70, half the temperatures are below 70. You bet, we've got that kind of mean, or that kind of median. All right, let's take a look at one more issue. Exercise number 3. A survey asked 50 third grade students how many times they had taken a shower in the last month. The data is shown below. The median is 17. All right, letter A. How many outliers do there appear to be? Pause the video now and see if you can answer this question. Well, unlike the last 2 examples, here we have 2 outliers, right? Because we've got this significant gap, and we've got this significant gap, so we've got 2, right? The one that's at 1, and the one that's at 35, right? So maybe you were like me as a 3rd grader and you didn't shower very often, right? Or maybe you're somebody that just loves to be clean. You're showering so often, you're showering more than once a day, right? So there's 2, and that is completely okay as well. You can definitely have outliers both on that low end and the high end. But this leads us to an interesting thing, because oftentimes when we have outliers, we're concerned about the fact that they could make our mean, our average, not really represent the central value of our data set. So let's take a look at letter B. Why would removing these outliers not significantly change the mean? So right, we talked about the fact that like in that first exercise, when we got rid of the chaperone, right, it changed the mean age from 8 years old, which wasn't very representative of the data set, to 6 years old, which was. But my claim is if you toss that thing out and you toss that one out, it wouldn't actually change the mean very much. Why is that? Well, it's kind of cool, right? It's because there's one on both the high end and one on the low end. So if you will, they kind of balance themselves out. You can almost think, if you've ever seen a seesaw / teeter-totter, right? You got the place where it's pivoting, right? The fulcrum, as we call it in physics, right? That's sort of the mean, right? It's the balancing point. Well, the one on the low end and the one on the high end kind of balance each other out. So, because there is both a low outlier and a high outlier, they balance, or you could even say cancel each other out. But I'm going to say balance. Balance each other out, right? So a high outlier is going to pull the mean up, a low outlier is going to pull the mean down, right? And if you've got one of both, they just kind of balance each other out. All right. Outliers are very, very important in statistics, right? They're data values that lie far away from the main cluster of data. Oftentimes easy to spot because there's large gaps in the data between those clusters and the outliers. Now, outliers are particularly important to spot because they can throw off your measures of center, especially the mean. They have almost no effect on the median, but they can really alter the mean. A high outlier making the mean go up, a low outlier making the mean go down. And as we saw in the last exercise, you could have outliers on both ends that actually then mean that the mean and the median don't significantly differ. All right, we'll see outliers here and there in our last lesson on statistics, but for now I just want to thank you for joining me for yet another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.